Well, so thanks everyone for showing up on the first thing in the morning after the banquet. I found a little bit of a stretch myself, so. Right, I'm going to speak today about one of my favorite topics, independent transversals, and especially in kind of considering the setting for this conference, I'm going to talk about some structural aspects and also some algorithmic aspects of this problem. So, what is this problem? What do I mean by an independent transversal? So here's the setting. You have a graph G, and you have a fixed partition of the vertex set of G. This is what you're given. And the thing we're looking for is a so-called independent transversal. So what's that? It's a set of vertices, and it's independent, so that means no edge of G joins two vertices in this set. And it's a transversal, so that means that every class in this partition, this fixed partition, contains exactly one of these vertices in the set. So that's an independent transversal. So here's a picture. There's a graph with a vertex partition. And the thing we're looking for is we want to be able to choose one vertex from each class so that altogether in the graph that forms an independent set. So here the red vertices are satisfying that property. There's no edge of G joining two red vertices. Okay, so that's the notion of independent transversal. This is a very kind of general notion, comes up in a lot of problems. So yeah, I wrote here, many combinatorial problems can be formulated by asking whether a given graph with a particular partition has an independent transversal. But indeed, almost all problems in some sense can be described like this because, for example, the SAT problem we can describe in these terms. So suppose we're given a Boolean formula like this one. Try my laser pointer here. Yeah. So here we have a bunch of clauses. Each one of them contains some variables written in as a variable or its negation. And we want to ask, does this have a satisfying truth assignment? It's a basic SAT problem. Well, we can formulate this as an independent transversal problem. And so here's how to do it. So for each clause, you put a vertex for each variable in the clause, and that's going to form a class. So this is going to be a class of 3 vertices, another 3, another 2, another 3 here. That's the graph. Those are the vertices of the graph. And what edges do you put? You just put an edge between every occurrence of variable xi and every occurrence of a variable not xi. Right, so every variable then is going to correspond to a component of the graph. And each one of those components is going to be a complete bipartite graph, touching each class at most once. And so that gives you a vertex partition graph. And the fact is that satisfying truth assignments correspond to independent transversals in this graph. So just thinking about the components, there's a typical variable, x and not x. You just join every occurrence of x to every occurrence of not x for every x. And from that Boolean formula, actually not the one I wrote, but you can imagine, you will get a vertex partition graph like this. I drew all the components corresponding to variables in different colors. And what is an independent transversal? It's a choice of one vertex from each class so that no two are joined by an edge. Just think of those are exactly the variables that you're setting to true. So if this is x, in its red, it's going to be true. If it's not a W, then a W is going to be false. And that's going to be a satisfying truth assignment because every clause gets something that's true. And the fact that it's independent tells you that you're never trying to call a variable both true and false at the same time. Okay, so that's just a little story to kind of demonstrate that the independent transversal problem is quite a general one. This SAT example is extremely general, and whatever I say about independent transversals here in the rest of the talk won't really say much in general about the SAT problem, but there are many other combinatorial problems that have a much more natural formulation in terms of independent transversals, and I'll mention some of those. Okay. However, of course, what this SAT story does tell us is that we can't expect any kind of efficient characterization of vertex partition graphs that have independent transversals. That would be too much to ask. So what we instead focus on is finding sufficient conditions which will guarantee that, that a vertex partition graph will have an independent transversal. So there are many examples, several examples of such sufficient conditions. Some are easier to verify than others. So for this talk here, I'm only going to focus on one of them, and it's kind of the easiest one to state, stated in terms of of parameters of the graph and the partition that are very easy to calculate or verify. Right, so my main parameter of the graph that I want to relate these things to is just going to be the maximum degree. So let's assume that every vertex in our graph now has maximum degree, has a degree at most d. And so here's a natural question regarding independent transversals. If I have a graph with maximum degree d, and I have some partition of its vertex set into classes, how big do those classes need to be in order for me to guarantee that I can find an independent transversal in the graph? And then I expect this how big number to be in terms of d. Okay, so how big in terms of d should the classes be to guarantee an independent transversal? It's a very natural question and was already introduced and studied a long time ago in the 70s by Bolobash, Erdős, and Szemeredi. And there are many further contributions to this topic by many people, and I'm going to, unfortunately, be rude and not really go through the precise details of this in order to save time. But there were lots of contributions, important contributions along the way. The answer to this question is a very specific one, and this is theorem 1, which I'm going to call theorem 1. Vertex partition graph, if every, with maximum degree d, at most d, if every class has size at least 2d, then this guarantees the existence of an independent transversal. So that's, in fact, a best possible statement, because actually, quite a bit later, after this theorem was proved, there was still active work on constructions, and Szabo and Tárdas gave an example for every d of a graph with maximum degree d, class size is 2d minus 1, that does not have an independent transversal. So this is exactly the right number here, 2d, in general. Okay. So this is quite an old theorem. It first version appeared in 1995. Has two proofs, a combinatorial proof and a topological proof. Topological proof came a bit later. And I'm going to talk about a couple of different aspects of this theorem, and both of those proofs are going to be relevant. Okay, so so as I said, it's quite an old theorem and describes quite a general situation, and so by now there have been many applications of this theorem in all kinds of areas, many applications in graph theory, lots of different coloring problems. There are very natural ways to express, for example, the list coloring problem as an independent transversal problem, many other types of coloring problems, graph partitioning problems, special independent sets. But also in other areas like group theory and ring theory and theoretical computer science, there have been a lot of applications now of this theorem. So this kind of provides motivation for asking, well, can we say anything more about this theorem 1? It just says you have this d, you have these class sizes 2d, and there is an independent transversal. So I'm going to talk about one kind of structural aspect of this question and one algorithmic aspect. And that's going to be my topic here. So first of all, the structural aspect. So here's a so-called stability question. Suppose you have an you have a vertex partition graph, maximum degree d. Maybe the class sizes are a little bit smaller than 2d. And you don't have an independent transversal. Can you say anything about the structure of the graph? I told you that the 2D was best possible, and the example of Szabo and Tárdas, the graph itself was a union of disjoint complete bipartite graphs. So one might ask, if you're in this bad situation, you're only just slightly unlucky, classes are slightly smaller than 2D, can you at least conclude that your graph is somehow close to being a union of complete bipartite graphs? as in the example, the extreme example? Well, you can ask that question, and then if you think about that question for a moment or two, you realize the answer is no. Because imagine you have a huge graph with all kinds of vertex classes, and it doesn't have an independent transversal. And there happen to be two vertex classes over here that are joined completely to each other. You can't even find an independent transversal in that tiny set of two classes. And then the rest of the graph could be whatever it wants. You're still not going to get an independent transversal here. So this question, as I wrote it here, is not really the right question to ask. A better question to ask would be, is there some subset of the vertex classes for which the graph induced on the union of those is close to being a union of disjoint complete biproduct graphs? That would be a more natural question. So this would say, for example, that in maybe some of these applications, if you happen to know that your graph is very far from ever being a union of disjoint complete biproduct graphs in any kind of subset of the classes, then if you knew something more about this question, if you knew the answer to this question, then maybe you could get some better results. Okay, so that's the structural question that I want to ask. It's this stability question. If your class sizes are a little bit smaller than 2D, and there's no independent transversal, what can you say about the structure? And the other question, which in particular for many applications is maybe more important, is the algorithmic question. So the proof of theorem 1, well, there are two proofs. Topological proof is completely hopeless with regard to algorithms. Combinatorial proof, it does give an algorithm for finding an independent transversal, but it's an exponential algorithm. So in all these applications, maybe you'd actually like to be able to find these independent transversals. So second question, if we are allowed to pay a little bit and maybe allow the vertex classes to have size slightly larger than 2D, can we, by paying a little bit like that, actually get a polynomial time algorithm, which will find an independent transversal for us? So from the algorithmic point of view, this would be maybe worth it to spend a little extra here. So to say that question in a kind of more quantitative way, how big should the vertex classes be in order to get an algorithm, an efficient algorithm for finding a transversal? Okay, so these are the two questions that I'm going to address, and I'll give you kind of, I will give you answers to both of them, and they are satisfactory to some degree, but maybe not completely, so I will say why. Okay, so the structural version, so again, we have our vertex partition graph. It has vertex classes of size a little bit smaller than 2D, maybe we have some epsilon, oh, it's not written there. Class is a little bit smaller, and we don't have an independent transversal. What can we say about the structure? The first question to ask there is if the classes have size 2D minus 1, exactly one less than is required, then do we know that really the graph is definitely a union of complete biproduct graphs, disjoint complete biproduct graphs? And the answer to that question is yes. So if you do look at the topological proof of theorem 1, then that does follow. So we know that the exact version of this kind of structural question is true. So which gives some hope that there will be a stability version also, that you can go a little bit away from exactly this number 2D minus 1 and still hope to see some kind of structure in some subset of the classes of the graph. So that's the exact version. So here's the stability version of theorem 1, which I will tell you about. So here's now our small epsilon. We are assuming that classes have size 2 minus epsilon times d each, but we do not have an independent transversal. Then here's the stability statement. So it's a structural statement. Then there is a subset of classes. So that on that subset of classes, you look at the graph induced by the union of those, and it is close in this sense to being a union of complete biproduct graphs. So this says that you have, another partition into S minus 1 pairs of classes. And between those pairs of classes, you see lots and lots of edges. So the number of edges in G that you've seen between these two classes differs from the maximum vi prime size by at most some function which depends on epsilon times the number of edges in the graph. So we have this at least from a distance, as long as these classes are close to 2D and we don't have an independent transversal, then really this structure does exist. So that's the stability, that's the structural thing I was going to tell you. And here's the algorithmic question. So again, this is the question again, how big should the vertex classes be in order to guarantee a polynomial time algorithm for finding an independent transversal? So that question, at least to get some quick answer to this, is not difficult. So if, for example, you allow the classes to be not 2D but 2ED, and E is really here E, the number E, not to do with the edges of the graph, then just using the local lemma, you can easily find an independent transversal, and then because of algorithmic versions of the local lemma, you would be able to find such a thing algorithmically. So if you're willing to pay this much per class, then this is definitely known. But maybe you would like to do better than that, and there is a sense in which we can do better than that. I will tell you this theorem. This is not the most general theorem I can tell you here, but it's the easiest to state again. So this is, I'll say it this way. It says, let D be given. So we're thinking of D now as being a fixed constant. So under those conditions, then we do have an algorithm, an efficient algorithm, which will find an independent transversal in your vertex partition graph as long as the classes have size at least 2D plus 1. So you just have to pay $1 more per class, as long as you're willing to do this for fixed D only, and you will find an independent transversal. And in time polynomial in M is the number of classes. So why the fixed D? Well, if you really look at the running time of this algorithm, you see it's you will get the exponent of M will depend on D, something like log D squared. Okay, so I'm going to tell you also about that theorem 1A, and I should mention that this one is part of a much larger project to do with algorithms and these questions, together with the Chulu Anamalai and my student Ali Graf. Okay, so those are the results. So now I'll tell you a little bit about the proof. I'm only going to kind of wave some ideas at you mostly, especially for the structural question, which involves some rather more complicated stuff. But the algorithmic question, I can really kind of tell you basically how it goes. Okay. So, right, so and as I mentioned, the original proof of theorem 1, there are two versions. There's a combinatorial proof, which is based on a kind of alternating tree or alternating path kind of argument. And the second one is a topological proof based on this idea, this notion of topological, so-called topological connectedness. So if I'm going to say anything about topological connectedness, I feel kind of obliged, although James didn't, so maybe you shouldn't feel obliged either to tell you the definition of this parameter of graphs. It looks terrible, but if you don't want to read this slide or think about it, just think about, I'm going to define some kind of unusual parameter of graphs, and then you can just not listen for the next few minutes. But for completeness purposes, I'll tell you what topological connectedness is. This is, by the way, a non-standard definition of it as well. But there's a reason why I write it this way, even though I'm not going to tell you the reason. So I'm talking about a graph, and I'm interested in independent sets in the graph. So I'm going to look at the so-called independence complex of the graph, and all that is the set of independent sets in the graph. And the set of independent sets in a graph is an abstract simplicial complex. All that means is if you have an independent set and you have a subset of it, that's also an independent set. So that's all abstract simplicial complex means. So for any simplicial complex, sigma, so for example, the one I'm writing here is the independence complex of a graph, there's this notion of k-connectedness, write it in this non-standard way to do with triangulations, but normally one talks about continuous functions from the sphere and extending them to the ball. But I'll say it like this. We say that the independence complex of a graph is k-connected if, for every d at most k, and this is, by the way, a different d, sorry about that, not the maximum degree of the graph, for every triangulation of the boundary of a d plus 1 simplex, so you have a d plus 1 simplex, and on the boundary you have some kind of triangulation T, and for every simplicial map from that T to your simplicial complex, so that means in this case, every labeling of the points of this triangulation with vertices of the graph, so that whenever you see a simplex in the triangulation, its set of labels should form an independent set in the graph. For every one of those, there's a way of filling up this triangulation to a triangulation of the whole simplex with another triangulation, and extending the simplicial map as well on that triangulation to the whole simplex. So whenever you can do that, for every d at most k, you say that the independence complex of this graph is k-connected. It's a rather complicated definition. And I'll associate some parameter, which I'll write like this, connectedness of the independence complex. And if you don't want to read that, just remember this is some parameter of graphs. And so what we use for this topological proof of theorem 1 is this notion, coming from this theorem, that says, in general, that if you have a vertex partition graph, and for every subset of the vertex classes, you look at the graph induced on those on the union of those classes, and you measure this weird parameter connectedness of the independence complex of that graph, and you find it's big. It's big in terms of the number of classes you took. If you can verify this for every subset of classes, then you can conclude that your graph has an independent transversal. So this is a kind of general theorem, and as you can imagine by reading it, the main challenge in applying it ever is to be able to estimate this connectedness parameter for a given graph. So I will tell you one tool that we know for estimating the topological connectedness. It's this theorem of Meshulam, which relates the connectedness of the independence complex of a graph to the connectedness of the independence complex of two subgraphs of it. One of them is obtained by deleting an edge, and one is obtained by so-called exploding an edge, the same edge. So these are two simple operations that you can perform on a graph. So if you can verify that the connectedness parameter is large for both of these things, then you can conclude that it's large for your graph J as well. And if you want to know what edge explosion is, well, it's written here in words, but in pictures it looks like this. Edge explosion means take your edge, and this is the operation you just remove from the graph. This edge, these two vertices, and all of their neighbors. It's kind of destructive, hence explosion terminology. Okay, so all I'm going to tell you about this structural result is that we use this parameter, and we use this tool to understand this parameter to be able to conclude the stability version. And I'm not going to tell you any more details because it's kind of hard to follow, and it's early in the morning after the banquet. Okay, but what is easier to explain, and so I will maybe spend a little more time on this, is the algorithmic question. So once more, where were we? We had this vertex partition graph. We had our vertex classes, which were now a little bit bigger, only by 1. So classes were size 2d plus 1. So we know there's an independent transversal, and we would like to be able to find it algorithmically. So what I'm going to first tell you is simply the original proof idea of the theorem, which gives an algorithm, but it's an exponential algorithm. You'll see it's a simple algorithm, but the running time is the bad thing about it. Okay, so here's the proof. So remember what we're doing. We have this vertex partition graph, and we're trying to find an independent transversal, which I'll call M in the whole thing. And suppose we went and we put in some vertices in M until we couldn't anymore, and we have some classes that, that don't have an element of the transversal. So we just, we take such an M, we do the best we could, and we have here a class U which is missed by this independent transversal. Of course here, there's a whole graph, a whole bunch of edges here which I didn't draw. Okay. So I just choose such an M and such a U1, say, this is the class. And I take any vertex V1 in this class, and I ask, does this V1 have any neighbors in this M? If it doesn't, then I'll just put it in and I will improve my M. So that's what I do. So this is what it says here. I choose V1 in my class. And what I'm going to do here is build a kind of tree. It says tree, but it's not really a tree. It's a kind of tree of vertices and classes in some complicated way. But I'm going to define some special set of vertices T. So I just take this V1, I put it in T, and I ask, is the degree 0? If the degree is 0, then I right away improve M. Easy. Okay, so maybe V1 has some neighbors in M. So there they are. And so otherwise what I do is I just, I'm going to extend my special set T. So I'm going to add to my set T the neighbors of V1 in M. That's the neighborhood here. The neighborhood of V1 in M, I put this into T. Okay, now my next step, which is also the general step, I look at what I have so far. Here's what I have so far. And I look at the set of all the classes that are involved in my tree T so far. Here they are, U. And I observe that because of the class size, remember the class size is 2D, how many vertices altogether inside this blue blob do I have? I have 2D times the number of classes. So 2D times the size of U. However, if I count the number of vertices I have in my T here, I find out that the number of vertices there is at most 2 times the size of U minus 1. And the reason for that is, except for the first class you took here, all the other classes contain an M vertex, so that's 1 for each of those. And then if you look from each one of those vertices, you look north, you will see at most one other. So these two, in fact, they actually see the same one. So I didn't even have to count 2 for this, but maybe this one had one up here, and maybe this one also had a different one here. So it's 2 times the size of U minus 1 vertices. I have so many vertices inside the union of these classes that what I find is, because the maximum degree is D, there is some vertex inside this blue blob that is not joined to any of these by an edge. Just because I have too many of them, and these ones altogether have 2D times the size of U minus 1 neighbors. And that's just not enough. So there's some vertex inside this set U, which is not joined to any of these. So let me choose one of those. I'll call it V2, or in general VI. And I'm going to add that also to my construction T. And then I'm just going to repeat this idea. So now V2, I'm going to look at it and I'm going to ask, does it have any neighbors in M? And if so, they would have to be out here, because we already know that this vertex is not joined to anything inside T. So we ask, does V2 have any neighbors in M? And if the answer is no, then what I do is I take out from the class containing V2 the M vertex, and I put into M instead V2. I can do that because it doesn't have any neighbors there or in here. And if I do that, I improve M. In what sense do I improve M? If you look at this picture, what I did was I lowered the degree of V1, who was the parent of V2, the parent of the vertex class containing V2. Right, so here was my picture before, and if V2 had no neighbors in M, I could just put it in M, take this one out, and V1 gets degree now 1. Of course, if V1 had degree 1 to begin with, that would be even better, because then I would get V1 as degree 0, and I would be back in the previous case where I immediately improve the size of M. Okay, so either way, I view this as an improvement of M, if I can do this. if the degree of V2 in this picture here is 0. So let's then suppose it's not 0. I would do that. And then otherwise, if I can't do that, I would extend this same idea. I would put into now my T all the neighbors of V2 and M, like that. So maybe now V2 has just this neighbor M here, over here in M. And that's my general step. So in my next step, I would consider all of these classes. And I would again observe, because the class sizes are large, and there are only so many vertices in my T, I will have a vertex which is disjoint from all of them, and I can add and improve. And I just keep doing this. And I can't do it forever. My graphs are finite. I can't do it forever, so I carry on building this kind of tree-like structure, vertices and classes, until, well, if I fill up the whole graph, well, then I have to start getting improvements. So one way or the other, I must be able to, in the end, improve all the way back to my original class and increase the size of M. And that's the algorithm. So it's quite a simple algorithm. Let's look at the running time. Running time here is where the bad news is. So if you think about how this algorithm runs, we can describe its progress by this kind of vector of numbers. I have a number for each class, or each class except the first one. And what is it? It's the degree of the vertex VI. And you saw that at every step, and I fill out, I have degrees of the vertices that I have so far, and then I just fill it out with the big numbers that are bigger than any degree. So at every step, if I increase the size of the tree, then I change one of these big numbers to the degree of something, so that gets smaller. Or if I have one of these improvements, then I lower the degree of one of these earlier ones. So every step improves, so reduces a lexicographic order of this vector. So it has length m minus 1. All of these numbers are at most d. And so, well, actually, yeah, you could take these 3d plus 1, say. So the number of steps I take here is, well, obviously finite, but unfortunately can be exponential, because if I really do this, kind of fill this up all the time, then I'm taking something like d to the m steps. Okay, so that's the original idea of the proof of theorem 1, and that's the algorithm. Simple algorithm, but this is the bad news about it. So now I'll give you a few ideas about how to make this an efficient algorithm by paying just one more vertex per class. And again, I'm just going to tell you the basic ideas. Not going to tell you the details precisely, but I think the ideas are simple and nice. Okay, so this is what we do is basically the same thing, but with some careful modifications. So the first one here, it says maintain layers. Now before, in my algorithm, what I did was, whenever I had one of these U's, I just looked in the union and I took any old vertex in there which is not joined to anything else in T, and I carried on with that one. This idea, maintain layers, again a simple idea, is to do this in a very systematic way. So whenever you're looking at such a union, what you do is you always take, if you can, vertices that are in the earliest class possible, a bit like breadth first search idea. So what this does is, so now this is meant to suggest that at the beginning I put in my vertex that had degree 0 in each step in the first class, as long as I could. And then I created a layer of classes under that. And then in this layer, I always tried to put vertices here rather than vertices that I found further down until I fill this up as much as possible. So that's the idea of maintaining layers. So for one thing, it's more orderly. You kind of you have these layers of new vertex classes in the construction. But also this will help us find out that the actual depth of this tree is going to be short. So that's the idea of layers. The second idea in my original algorithm, whenever I found a vertex whose degree in M was 0, I put it in and improved my construction. Here what we do is we are more patient than that. So we wait until a particular layer has built up some significant number of vertices whose degree into M is 0. And significant number here means a positive proportion of the size of the layer. And I measure that positive proportion by some small positive constant, which depends on D. So I do these updates, or improvement updates, only when I can do a lot at once, when I can do a batch job, as it were. And the third modification is whenever one of these updates happens, then some things are going to disappear from the tree, and we might be able to rebuild an earlier layer, and we also do that only when we add some significant proportion of that layer. Right, so I showed you the picture of maintaining layers. What about this update? So now imagine here I've built this layer of the tree, and so I filled up as much as possible these ones. And now I have this layer here, and I'm now constructing the next one. And during the construction of the next one, I actually find not just one, but a lot of vertices that have degree 0 in M. Those are these ones. So this big clump, this is what I only do the update in clumps. So what does the update look like? Well, again, for each one of these, I'm going to take a vertex that has degree 0 in M, and I'm going to put it into M and take out the M which is in that class, so we get a picture like this. And now all of this stuff is going to disappear from the tree because it's not connected anymore. And I'm also going to discard all the rest of this layer. So this whole layer, and now I'm just going to throw out completely. It's gone. And so here's now the previous layer. Previous layer is really down to only these two classes. Still have all the vertices, the black vertices that I used to have, but here I only have these two classes. But now that a bunch of stuff has disappeared over here, maybe I can carry on and make this layer bigger. And the third requirement is that I do that, but again, only if it increases the size of it substantially. So I maybe can add a bunch more stuff, but I do that only if I can do quite a lot. Okay, so those are the three new ideas to add to the original proof idea of theorem 1. And let me just tell you briefly what these things do for you. So this maintaining layers, this has this effect. So remember again that the classes have size 2D plus 1. Remember in the original theorem, in the original argument, the union of a particular bunch of classes U was just big enough to tell us that there was some vertex that we could add. Now, whenever we take some union of classes U, there's going to be quite a number of new vertices we could add. And these are going to, and if I make the tree bigger and bigger and bigger, this kind of bunch of vertices I can add is going to build up somehow. And this policy of maintaining layers has this effect that all those available vertices are going to get pushed to the bottom all the time. So the vertices that are undominated, that don't have any neighbors in the tree so far, are going to be kind of pushed all the way down to the bottom layer here. And so this is going to have the effect, as long as there are no updates, it's going to have the effect of making the tree, the number of undominated vertices here, be a positive proportion of all the vertices in the tree. And so at each step, each layer is going to grow by some little constant times the total number. And so that's going to be an exponential growth. So this thing is going to grow exponentially by some small but 1 plus delta base of the exponent. And so this is going to tell us that we cannot do this forever, but not only can't we do it forever, we can only do it for about a log number of steps. So the depth of this tree is going to be logarithmic in the number of classes at most. And this is a very important, has a very important algorithmic consequence. That somehow you see everything in a short span there. Doing the clumping, so the updating in clumps and rebuilding layers in clumps, I will just tell you, allows us to have a different kind of signature vector. So the signature vector I showed you before had an entry for every vertex in the tree, or half the number of vertices in the tree. And that's way too many. We don't want to maintain that amount of information, but it turns out that doing these updates in clumps allows us to have a signature vector that instead measures just sizes of layers, so instead of individual degrees of vertices. So every growth of layer step, the basic one or the type 3 one, if you think about those pictures I showed you, these things either increase the number of non-M vertices in a layer substantially, that is by a positive proportion, or decreases the number of M vertices substantially. And because of these kind of substantial changes, it's possible to describe the progress of the algorithm by a signature vector, which is just a couple of entries per layer, and each one of them we can measure by an integer increase in a log function. And so by means of this, we're able to get a signature vector which is, well, first of all, short. It's only logarithmic length. And the actual numbers we get in it are not large, and they're well controlled. And so I will just tell you that it's possible by using these features to find something that gives you a polynomial in M, running time. But the polynomial, well, it's like this. It's M to the something depending on D. So order of log D squared, something like that. So this is why it's still, for this discussion, D being constant is kind of necessary. Okay. So that's about all I'm going to tell you. I will just, well, I said that there are various more general things here. I talked here in terms of just maximum degree. But in fact, what's relevant in this argument is not maximum degree, but really just a domination. So we were always saying, well, we have some subset of classes, and because of the maximum degree, because of the size of the classes, there is some vertex which is undominated by the construction that we have so far. So really, you can state this all in terms of domination and say that the algorithm really does this. It finds either an independent transversal or it finds a set of classes that has a small dominating set. There's some small number of vertices inside those classes that dominates everything in the union of those classes. So we could say it in that way instead, which is a more general way, and in some applications that's definitely better. Dependence on D, I just talked here, I didn't tell you any other parameters, but if you refine this idea by introducing some different parameters, actually that exponent of M, which I wrote as order log D squared, could really be replaced by something else which measures not just the maximum degree, but something much more restrictive, the maximum number of independent neighbors in distinct classes that a vertex can have. So you really have this dependence not really on D, but rather on this R parameter. But I would comment further that we don't actually know, so this is, as I mentioned, very much work in progress, and we don't know at the moment whether that exponential dependence on R is essential. And our hope is that it isn't. It's somehow an artifact of the way we measure the progress, and we hope that this can be improved also, and to remove this also. Okay, so that's all I have to say. Thanks for your attention.
All right, are there any questions? Tony?
Can you say a bit more how you estimate that connectedness parameter that you defined? Like I thought there's some game or something?
Yes, so you can view it in terms of a game. That's true. Should I page back through this? Well, yes, so some people like to describe it in that way. Here. So, right, this is a way of, this is the principal way that's used, actually. Right, so this just says, you have any graph, you want to estimate the connectedness of the independence complex of it. You can take any edge, and if you can confirm, which usually you can't, that if you could delete this edge, you have high connectedness, and if you explode it, you have high connectedness, then you can conclude your graph is K-connected. But of course, you're in the beginning starting with an arbitrary graph. So, so some people like to describe this in terms of a game as follows, that you choose an edge, and you hand this edge, and you point to this edge to your enemy, and your enemy decides whether to delete it or explode it. So you don't know what the outcome of that is going to be, okay? So you're starting with the assumption that your graph does not have high connectedness. So if it doesn't have high connectedness, then one of these also doesn't have high connectedness. And he's going to tell you which one doesn't. But you don't have any control. Right? And so then you have this already now fork, and then you're on one side or the other of this fork, and you again would choose something. So typical argument is you look at the graph in the beginning and you have some kind of policy of which edges you're going to present to your enemy, but of course after a while maybe some of those have disappeared because of some explosions. Yeah. So this is a way in which it can be viewed in terms of a game. Yeah. But yeah, in general it's a hard thing to estimate. That's the upshot. Yeah.
Is that a corresponding problem for Matroid? So you have a partition in Matroid?
There definitely are corresponding questions about matroids and interesting ones. And I'm not entirely up to date on those, but some people in the audience are more, and they will even maybe talk about such things shortly. Yes? Yes, so for questions about related to this about matroids, I especially refer you to Hansif. Yes? Yes?
Just think about the case when the class of size exactly 2D.
Yes.
I mean, if D is very small, can you do it in polynomial? Like if D is 1, you can.
Yes, if D is 1, you can, but already if D is 2, so if you, so if D is 2, could you really, so you have classes of size 4 and D is 2. Could you do it in polynomial time? Not immediately from what I just said here, but maybe because of some special circumstances, although, yeah, I don't, and if you further know that there is no independent transversal, then you know that everything is a C4. So the classes of size 4 and the graph is a union of C4s. Could you find it in polynomial time? Good question. Possibly. Yeah, but not immediately. But yeah. Yeah, it might be possible in a very restricted case like that. Yeah, but it would be definitely ad hoc arguments. Yeah.
Any further questions? If not, it's time for a coffee break.